Good afternoon, Calculus BC. I hope you've already started working on your My Math Lab, which was kind of like extra practice from the homework from day one. Putting together some polynomials of the Taylor flavor, and then some at Maclaurin. Hopefully, you know the difference. What I thought I would do here is show you in your textbook the PowerPoint slides they have that went with what we've already done, and you'll understand why it's not too impressive, because it's not like the other slides that I throw in at you that I've already done. But it is chapter 10 of the book, and the actual lesson you already had. Well, you've already had every lesson: 1, 2, 3, 4, 5, 6, 7, and 8. 1 through 7 was all the convergence tests. Okay, big part of Taylor polynomials and sequences and series. Some of them were Taylor, most of them were geometric, or just other sorts of series that we created. In 10.8 of your textbook, this is where they start the Taylor and Maclaurin series. And this is the review from day one. Basically, the summation to infinity. And you'll notice that k is what's changing. So you're going all the way. So you're going to get, if you look very carefully, you should see it. That stands for the zero derivative right here. If you plug in 0 here. What did I write? It's not checked off. There it is. 0, if you plug the 0 in, get the zero derivative of a, whatever a is the center of your, what value are we considering, like around 1, around 2, around 3, could be 0, okay, and x minus the a value. And that always increased at the same exponent as the derivative. The 0, 1, a 2, a 3. That lined up with what derivative you're at. Divided by k factorial, 0 factorial, 1 factorial, 2 factorial. This is just a review of what we've already had in the previous lesson. So as you're building this polynomial, okay, a Taylor series allows any a value. Maclaurin is when a is a 0, but they can all be called Taylor. So f of a, because once you plug in your a, if it's a 0 derivative, well, 0 derivative, it was just a function, okay? Here's your first derivative, obviously x minus a to the first, and this was divided by 0 factorial, and this was divided by 1 factorial. It went on to your second derivative at a. Your second derivative substituted a, x minus a squared divided by 2 factorial. And you keep on going till you get to the final nth term. But it never really ends. There's n plus 1, n plus 2. You could keep on going past n. N just is an arbitrary value way in the future. So in Maclaurin series, x happens to be 0. X, you're looking for a round centered at x is 0. So it would make sense that every time you plugged in a 0 for a, it's the same thing. You just got, in this case, f of 0, because a is 0. And then here, this term here, the reason that happens is because x minus 0 is still an x, and then you got f, the first derivative, at 0. of x. There's the x that came from this part right here. So we just continue it. So you have to be very competent at creating your series. You have to know what your function is. You have to know what your function is evaluated at that a. You have to know what the first derivative is of that function. You have to know what your first derivative is at that a. And you're going to keep on going and go to your second derivative at a, so forth on. So that was the review of that. Let f, this is your definition of a Taylor polynomial order of n. In other words, if you kept on going as far as you can go, the last number you can think of is n, even though there's an n plus 1, n plus 2. But let f be a function with derivatives of order k. In other words, you're going to keep getting the zero derivative, the first derivative, the second derivative, and so forth. And we're going to stop at n. Not that it really does stop, but it can only go so far. I mean, we're only human. I mean, we're going to maybe go to the 10th term, the 11th term, the 12th term. Even, what if we stopped at the 4th term? That's not unusual. You just got to decide what n's going to be and how many terms are you going to use to be accurate. And you should have explored the graphs already of partial sums and found out that when you're looking around a center like 0 or 1, you didn't need a whole lot of terms to have some pretty good accuracy. So we got f of a. That's normal. We talked about that. First derivative at a, x minus a with the first power. The second derivative, 2 factorial. We showed how that 2 factorial was always a part. X minus a squared. Blah, blah, blah. And then he decides to go to using just some k now. K is another number. And then afterwards, there's more terms. And then here's my final resting place that I decided. N was 4, N was 5, or N is 10. You have to know this nth term. It's generic. I mean, if they ask you for the quadratic term, then you know you're going to have to go to the second derivative. Or the fourth, if you want the fourth power, you got to go to the fourth derivative and so forth. This was a graph that talked about polynomial with the linear term, only to the linear term. Then it went to the quadratic term. Then it went to the cubic term of e to the x. And you've already built e to the x several times. And our center was at 0. So if you look right here, you can see clearly at 0 that every one of those look like a very good approximation around 0. What you're going to do in the next lesson is we're going to talk about this circle here. And you're going to talk about a radius of convergence. Obviously here, you think that's a radius of a circle. And that radius is the same as that radius. So there is an optimal radius of convergence that we like. E to the x is very nice because even with the cubic polynomial, we are very close to sitting on the curve e to the x, which is, I can't tell if it's the blue one. I think it's the blue one. I think the blue one is the true e to the x. Every one of those look pretty good around 0. If we were to do the Taylor series around x is 1, then what would happen is you would probably get a very good fit around the 1 place here, if that was important to you. What were they doing here? There's the nth term, polynomial, but in this case, he has a -1 in front, which means this is a weird one because it obviously has a switch that gives you a positive, negative, positive, negative, positive, negative. He, he he's giving you a heads up that this one converged to cosine. Oh, okay. Yeah, we built that one before. And if you look at your higher ones, look at, I'll go to the blue. Well, the blue actually is cosine. Check out this green one. The eighth degree. Let's see, I'm going to trace it up the green. The green, if I can keep it on the green. Well, was that the green? There's another green in there, but this is the green I want. That green's doing pretty good. It's a pretty good approximation. I was writing it, so 8 terms was very good. Reason why they had a switch was because the derivative of cosine flips every time, or at least every third. They could even do a piecewise. It's e to the -1 over x squared. It's flat at the origin. That all the derivatives there are 0. So there's an interesting convergence there. That was it. That would have been all that's all the PowerPoint gives in your college textbook. So the other PowerPoint that I used comes from a more lower level calculus textbook for high schools to use in the AP world. And they tend to be a little more simplified, which is why I use them. All right. Here are the note pages for day 2, and I'll be posting these online for you so you can follow along if you should be doing. Definition of the nth term degree polynomial. It obviously was already mentioned in that section of your college book. Should be nothing new here. F takes n derivatives. So the letters change. X equals to C is the center. So they're just doing a generic Taylor polynomial. F of C, F prime of C, F double prime of C. Now you see that 2 factorial is important. 0 factorial wasn't important. 1 factorial wasn't important. 2 factorial is. So F double prime at C over 2 factorial is the constant in front of x minus c to the second power, plus the third derivative over 3 factorial at c, x minus c to the third. Then he skips a whole bunch and jumps right to the very, very end, which we just talked about, this exact same one. Whatever derivative you're at, remember, you have to decide how far am I going to go. That c, that n, lines up with what degree you want. How many terms do you want? Okay, a little bit of history. Brooke Taylor. He's the one that came up with this. Thank you, Mr. Taylor. Mr. McLaurin wasn't going to be outdone, and he gets credit for saying, what if I just set it at 0? Let's keep it simple. But that's why we use them both. They're all Taylor, though. So if you have at 0, it's the same thing we just talked about, except now we know exactly it's at 0, and their x minus a is always going to, x minus a is always x minus 0. So therefore, it's the same thing. To use Taylor polynomials effectively, we need a way to estimate the size of the error. Yeah, we already hinted to this, but we're not going to use it today even. He just talks about the Lagrange in this particular set. This is provided by the following theorem. This isn't new. I did have this in my other slide. you've got your Taylor polynomial climbing, climbing, climbing. And the nth term is where we stop. And we know that I could have a billion zillion more terms. And all those terms in the future would keep adding up. But if we just add the error, the remainder, which is everything else past this one, that's called the remainder. It's everything after your 5th degree, your 10th degree, whatever it is. And the formula that we talked about last week was that the remainder is always going to be evaluated. There's some z value. Z just stands for an x value that is away from the center, obviously. But it's some x value that is, typically you want the smallest x value that would approximate our error to a certain amount of accuracy. And so we tend to use the next term after the one that we stopped at. If we stopped at x minus c to the 8th degree, that would have been the 8th derivative evaluated at c over 8th factorial. If that's where we stopped, then we know that the next term would be our remainder, which should be n plus 1. So that would be an x minus c to the 9th. And we would hope that that 9th derivative evaluated at c over 9th factorial, that there's some x between here. It may not even be, it's a mysterious value. But if we had this term, we know this term is probably bigger than the rest of the sum altogether, because this thing's going to get smaller and smaller and smaller as you go to the right. So this term is going to be a pretty good indicator. And that's what they're saying here. All right. Okay, he continues. The remainder has to be less than or equal to the maximum of f n plus 1 with some value, where maximum of n plus 1 at some value is the maximum value of that derivative between x and c. Okay, so it still sounds mysterious. But it does give you, when you write it like this as an inequality, it does give you like a plus or minus bit. So you have your x value and you have your plus c and you have your x minus c. So you do have an interval there. The fancy word is Lagrange. Lagrange, another mathematician. We're not going to use it today, but I hope it comes up again. We'll probably look at an AP problem. This is really something we should be doing together in class, but wow. All right, so this is P of 2. This must be a polynomial, a second degree. And so generically he wrote a plus bx plus cx squared. It's a second degree Taylor polynomial for f about x is 0. How do I know? There's nothing being added to x. What are the signs of a, b, and c? Okay. He wants us to use this picture. Now remember, a is just a constant. And so if you look at that picture and think about what's happening at 0, all that I know is that f of c, because that's what that would be. A would be f of 0. He's asking me for what's the sign. Well, it's above the x-axis, so I know that's going to give me a positive sign. B is the linear term. And where does that come from? first derivative. And we're still talking about 0. So look at 0, go up here, first derivative. Well, that looks to me like that derivative is a positive slope. So it also is. So b, which is related to the f derivative at 0, is also positive. C is coming from the squared term. C has to do with the second derivative evaluated at 0. Second derivative has to do with the second derivative test for concavity. That's concave down. So C is probably negative. So I'm going to go with A plus B minus C. Wasn't too mind bending. Suppose that the function f of x is approximated near x equals to 4 by a third degree Taylor polynomial. Okay, so he has it all done. And so there's my A, there's my B, there's my C. A is f of A, to remind you. B is f prime of A divided by 1 factorial. C is f double prime at A divided by 2 factorial. That's just to remind you. And guess what? A is always going to be a 4. Okay, stare at that for a second. So when I look at f of 4, f of 4, what do you think it's going to be? No mysterious, it's 2. Because that was my A term right here. That's my coefficient. That has to be from the function. This one comes from f. This one comes from f prime. This one is my f double prime. Oops. Sorry, this is my f double prime. I don't see an f. I don't see a to the first power with an x. Almost messed up. That would mean that f prime at 4 must be 0. Because there is no term up there. Ooh, it almost tricked me. F double prime at 4. Remember, f double prime at 4 over 2 factorial has to be the negative 5. Solving that for f double prime of 4, I get f double prime of 4 must be a negative 10. Okay, got one more to do here. Let me squeeze it on this side. Change my color. F, wrong one, triple prime of 4 over 3 factorial must be the coefficient 8. Therefore, solve that for f triple prime of 4 must be 8 times 3 factorial. 3 factorial is 3 times 2 times 1. 3 times 2 is 6. 6 times 1 is still 6. 6 times 8 is 48. So you can see how I'm actually building, or I actually took what was built. I mean, that's how I would build it myself. That's how I would get the same answers. B, does f have a local maximum or local minimum, or neither at x is 4? well, let's see. How do I do local max or mins? Well, I would definitely look at my f prime f4. And f prime of 4, let's see. It is equal to 0. That's good. That means it could be a relative max or a relative min. My second derivative, remember what we used to do? We would take the first derivative, solve it for what x value makes it 0. We obviously found x is equal to 4 was 0. Then we took our second derivative and we would plug in this critical number. That's a critical number. We would plug that in. So I'm going to plug in my 4 and we would check for the sign that it is. Since the second derivative is negative 5, which is less than 0, that means the function was concave down, which implied it looked like this. So what did we just find? We found that at x is 4 is a relative max on f of x. That was special. That was fun. The function f has derivatives of all orders of real numbers of x. Assume that f of 3, which is my a, is a negative 4. And my b is a 2. And my c is a 7. And my d is a negative 5. Write a third degree Taylor polynomial for f about x equals to 3. Good news. We went to the third derivative. That would give me the third degree polynomial. So p of degree 3 of x is negative 4 plus the first derivative, 2, divided by the first factorial, 1 factorial, times x minus 3 to the first, plus the square term is a 7, and it's divided by the 2 factorial, x minus 3 squared, plus the cubic now, which is going to be the negative 5. So if you don't want to put plus negative, you can, I'll erase it and put minus 5 over 3 factorial x minus 3 cubed. Now, that's my f of x. That's my f of x polynomial. So I could have said, is my f of x, which is a third degree polynomial. Write the fourth degree polynomial for g using f x plus 3. So what I'm going to do is, it's a composite function. Everywhere I see an x, I'm going to plug in an x squared plus 3 and see what happens. So g of x, which will be a fourth degree, the negative 4 doesn't have an x in it, so it's still going to be a negative 4. Plus, when I take the x squared plus 3 in place of the x, I get a 2 x squared plus 3. Don't forget my minus 3 that I already had. Plus, then 7 over 2 factorial. Again, in place of the x, I'm going to write x squared plus 3. But don't forget I had a minus 3 already there. And that's to the second power. And maybe I'll be convinced to keep going, but because I realize this is only a cubic, and then the next thing is going to be a 4th degree. Is that how far I want to go? Well, be careful. Slow down. You're moving too fast. You got to make the morning last. Just skip down the cobblestone, and you know the rest of the song. Look right here. Let me simplify. Negative 4 plus 2 x squared, because that's gone, plus 7 halves times x squared squared. Do you feel it? Do you see what's happening? I would have done too much work, and I'd have said, oh man, too many terms. So I'm done. Negative 4 plus 2x squared plus 7 halves x to the 4th. Da-da! So there's the lecture notes that I'm going to post up before even the video. It's going to take me an hour for this video to even get converted and then post it on YouTube. Lecture notes. There's a worksheet afterwards. This unit from these papers, the one you've already submitted as homework, and I still have to finish grading it. I don't know if I finished it. Can't remember. I'm getting so lost. Came from probably one of the most premier Calculus BC workshop instructors. She does almost all of them that happen in Texas. I saw her twice at Rice University, and Mr. Ramos saw her at Rice University once too. What's after this set? The worksheet, your homework. If you look at the end of the let's just see if there's anything in here that looks not the same. Looks like the same thing I've talked about. Same thing. Looking at the picture. Talk about the signs. There's 4 of them there. Right. Oh, this is review. This is a review of lesson 1. How to write it. I want to see the work. I know there are Taylor series creators online. That's not what we're about. You need to do those orders of derivatives, and only 2 people showed me the work on that last homework. 5 or 6 of you had answers, but only 2 of you proved it to me that you knew what you were doing. Then you have right, they gave you all the coefficients. You got to divide them by the correct factorials to create the 3rd degree. This is right off my lecture. 2011 BC problem. Now, this is what you guys did last time. I saw people have solutions that just basically came from the College Board. Guys, when they look so pretty and just basically no decoration, then I know you just got it online because they just put the facts. And that's not how the solutions on the College Board are not the way a student would have written them. They were like, here is the black and white nitty gritty. That's it. And you're only cheating yourself if you don't work them out first. I really want to see what you did. If you, I mean, anybody can Google this. But what did you do first before you Googled it? That's what's important. Everybody gets credit for this problem, but I would really love to see what you did with it. Challenge yourself. Is there anything else? No, this is it, guys. I'm going to post the homework with it, and I will talk to you on Wednesday. Please be safe and take care of each other. Adios.